Hi everybody, welcome back to Kitchen Physics from Mrs. Buelson's Kitchen. We're going to look at electric charge and the force between charged particles today, mainly using the electroscope I began to demonstrate in my first lecture about electric force. You didn't get a very good look at the electroscope and the video was acting strangely delaying. So we'll do a little closer look today. And then I'm going to talk about an at-home, in your own kitchen physics experiment that I'm assigning for you to do over the weekend. And we'll have a live meeting on next Tuesday and you can show us your experiments. You're doing your own kitchen physics. So if you remember, this is the electroscope. It's a little bit different than the electroscope pictured in your textbook. It's just a different style, but it does the same thing. There's the aluminum plate on top where you introduce charged objects. There's an aluminum cylinder around the outside, and this is effectively trying to shield other charged objects from the needle inside. There's the aluminum plate connected through a screw and some nuts and bolts to this like middle vein, and then resting gently on the middle vein is what looks to me like a straw covered in aluminum itself, and it can pivot on an axis. So when I bring a charged object close, so I'm charging the PVC rod with an old wool sweater. When I bring a charged object close to the electroscope, you see the needle deflect, indicating that a charged object is present, where in this case, the PVC rod is charged negatively. So those extra electrons are able to push on the electrons in the top plate or in all of the metal conducting surface, and the extra electrons on top push electrons down into the needle area, down into the vein in the needle, and since the needle is free to rotate and like charges repel, extra electrons in the vein and extra electrons in the needle repel each other and the needle deflects. So if I have more charge in my charged object, I get a larger deflection. If I have less charge, I get a smaller deflection. The markings on the inside of the electroscope are every 10 degrees. So you get, you can almost do a quantitative measurement of the amount of deflection, which is directly related to the amount of charge present. We won't get that technical, but it's the general idea. Okay, so first we want to look at how different objects interact with the electroscope, how we might charge different types of objects, and I have a number of things around in my kitchen. Then we want to look more closely at charging an electroscope by contact, so how that works and what it looks like. What happens when you bring then a charged object near an electroscope that's been charged by contact, and then finally charging by induction. So charging by having an object that is charged near the electroscope, but not by touching it, instead by grounding the electroscope. In the lecture, I talked about the process of grounding, where we're using this idea that the Earth is so massive and so huge that it's always electrically neutral. So if I have an object that carries extra charge and it's in contact with the literal ground, so in contact with the Earth in some way connected to the object. So in this case, my feet and my body are connected to my floor and my floor is connected to the Earth. So in any case, we're touching a charged object to the Earth. If it's negatively charged, the extra negative charge flows into the neutral Earth, and if it's positively charged, extra electrons flow up into it or are attracted into it because opposite charges attract, the object becomes neutral. Let's look at some objects and see what kind of interactions we can get. So I just showed you a PVC rod, so plastic type stuff, and wool. If I rub them together, I'm allowing these two objects to come in contact, these two substances to come in contact with each other, and if I rub it enough, I can start to hear crackles. So PVC or plastic, most plastics, are of a chemical makeup, the molecules are of a chemical makeup such that they can accept extra electrons in their valence shell. More chemistry than we need to know, but accepting of extra electrons, and furry stuff like wool or hair is chemically composed so that it tends to give up some of its valence electrons. So when they come in contact with each other, the energy of rubbing them together allows a transfer of electrons from the giving up electrons to the accepting electron substance. So the rod is negatively charged, and I can tell that it's charged by the deflection of the needle. I can't tell what kind of charge it is by the deflection of the needle. I need to know more about the chemical structure. I should also be able to bring the sweater close and show a deflection as well. So I get the same deflection, and I set it down on the counter, so it may have discharged. Yeah, it did. Oh, not quite. I get a deflection of plastic. I get a deflection with wool, and it's exactly the same deflection. So that's not enough to tell type of charge, but it's a way to tell amount of charge and the presence of charge. So what else could we do? I have a glass rod here. So let's see if glass and wool interact the same way that PVC and wool interact. So rub vigorously. I'm not hearing that same crackling sound, and I'm not seeing deflection of the needle. I think I accidentally charged the electroscope. I'm not seeing deflection of the needle with either the wool or the glass. So glass doesn't seem to interact with wool the same way that PVC interacted very strongly with wool, right? Or strong evidence of interaction. I saw neither of those deflections with glass and wool. What else? What about a balloon? In your do-it-yourself videos, you will have an option of working with a balloon. So we could try maybe a balloon and sweater, right? Balloon and woolly sweater. Do I get a deflection? Sure. And even a bigger deflection. So maybe there's something about the surface area. The balloon has much more surface area than the PVC pipe. Do I get a deflection from the sweater? Oh, I think I allowed charge to jump to the, ooh, it's very, did you hear that crackling? What about, so let's discharge this balloon. What about hair? I told you, fur, hair. Let's see if we get a deflection. Yeah, we do. So I was a little worried because I put some anti-frizz stuff in my hair this morning. So sometimes that can affect your ability to charge from hair. So wool, hair, PVC type plastic, balloons. What else? I have a small piece of silk and PVC. So let's see if we can get an interaction there. Not really. No, I don't see any deflection. Let's look at a close-up now of the electroscope, and we can talk through charging by contact and charging by induction. So in the close-up, you'll just see my t-shirt and maybe some of my chin, but you can get a much clearer view of the electroscope. So here is our electroscope. You can see the markings now, hopefully clearer. You can see that they're every 10 degrees. So we'll do again charging of, so I'm using the PVC rod and the wool. That seems to be very effective. And I'll bring that charged PVC close to the electroscope. Of course, it takes a moment for the electroscope to stop bouncing around, but you can see we get a deflection of something like 50 or 60 degrees. The sweater, trying to hold it the same distance away, of course, because the amount of force on the electrons in the electroscope depends on distance. Seems to be a little bit less, but it's also getting less as time goes on. So you're losing your charge either by grounding or by the polarized molecules of water that are suspended in the air accept an extra electron. So they will pick up electrons from a negatively charged object, and then they will deposit them on a positively charged object. So humidity can really mess with your electrostatics experiments. Let's look at charging by contact. So I have my wool, and I'm rubbing my woolly sweater with the PVC pipe. I bring the PVC stick close to the electroscope. The needle deflects. If I now touch this PVC stick to the electroscope, I'm allowing the extra electrons on the PVC stick to transfer to the metal components of the electroscope. And the needle remains deflected when I take away the PVC pipe. So I've added extra electrons to the conductive parts of the electroscope. Those extra electrons are mutually repelling each other. They're getting as far away from each other as they can. They're spreading out. And so as they spread out, some extra electrons go into the vein, they go onto the needle, and the needle, of course, deflects from the vein because those negatively charged objects repel each other. So what happens if I bring a negatively charged object close to my already negatively charged electroscope? you see that the needle deflects more, right? I'm pushing even more electrons into the vein and the needle. Well, what happens when I bring a positively charged object close to the electroscope? Right? Negatively charged electroscope with mutually repulsive negative vein, negative needle, and I bring a positively charged wool sweater close to the electroscope. What's it doing to those extra electrons in the vein and the needle? Opposite charges attract, so the vein and the needle have extra electrons, but now I've brought something positively charged nearby, which is attracting extra electrons up towards the plate. So if I bring it closer and closer to the plate, I'm more and more neutralizing the needle and the vein. If I take it away, the needle deflects again. So my negative charges are now spreading back out. There's no other forces on them except their mutual repulsion. And the needle deflects again. So let's ground this and try charging by induction. So I'm touching all of the metal parts to make sure that I can ground it. Again, grounding it means that I'm allowing those extra electrons that were in the conductive parts of the electroscope to flow into the earth. The earth acts like a sink for extra charge. I'm going to do the same thing with the wool and the PVC stick. I'm charging the PVC stick by rubbing it with the wool. I'm going to end up with a negatively charged PVC stick and a positively charged wool. Here is the negatively charged PVC stick near the electroscope, but not yet touching the electroscope. Instead of touching the electroscope with the PVC stick, I touch myself, my hand, and now I remove everything from the vicinity of the electroscope. And you can see that the needle is deflected. So I was bringing negatively charged object close to the electroscope, and we now know that that causes negative charges to flow into the vein of the electroscope. I've pushed electrons around. I brought electrons close to the top and pushed them into the vein, so the vein deflected. But then I touched the top of the electroscope. I grounded the electroscope. I've brought the negatively charged PVC pipe close to the top of the electroscope. Then while that negatively charged PVC pipe is close, we know that negative charges repel, so the negative charge in the PVC pipe is pushing negative charges around in the metal. I bring my hand in and ground it. So by grounding it, even though I'm grounding it at the top and not the bottom, those negative charges are trying to get away, the moving negative charges in the metal are trying to get away from the charges I've brought near with the PVC stick, and they exit the electroscope through to the ground because I'm touching it. So I have negative charges nearby, pushing negative charges away. I touch the electroscope and allow those negative charges to get even further away, right? Like charges repel. I then take away my hand, the ground, and the negatively charged PVC pipe, and we see the needle deflect. So the question is, what charge is the electroscope now? Is it positive or negative? Now that I've pushed negative charges away. Well, let's find out. So I can recharge. I've been talking a lot. So I can recharge the negative PVC pipe, and I can bring it close to the electroscope. Oh, interesting. Right? It's the exact opposite of what happened when I charged by touching. So when I bring the negatively charged PVC pipe close to the top of the electroscope, the needle goes back to straight up and down. When I take it away, the needle goes back to its original deflection, or its deflection when it was charged. Opposite story when I bring the sweater close, right? When I bring the sweater close, the needle deflects more. So we're remembering that the rod gets charged negatively, sweater gets charged positively. So when I charge by induction, the opposite effect occurs as when I charge by contact. Let's think about which charges are which then. I'm not going to answer it for you. We'll switch now back to the big camera. So you've now seen a demonstration of charging an electroscope by contact and charging an electroscope by induction. It's going to be your turn to do some kitchen physics or house physics or backyard physics or whatever you want to call it of your own. So I'm giving you 5 options, and links for the instructions are in Canvas in this post. Your options are electric slime. We're calling it electric slime. And for that, you're going to need cornstarch. It's called corn flour in the instructions because the instructions were produced by some physicists in Britain. So cornstarch, you'll need vegetable oil. I think any cooking oil will work, whether it's olive oil, vegetable oil, Crisco. Well, it needs to be liquid. Maybe ask your parental unit or whoever's in charge of your kitchen before you choose the most expensive olive oil. And you will need a balloon, if you have one. We now know that balloons and PVC work kind of the same, so if you can find a little piece of PVC pipe or polystyrene, so foam type packing material. Those are your options for electric slime. You're also given an option of bending water, and for that you just need your hair or a woolly sweater and a plastic comb. Your third option is called spin a straw. So for that you're going to need a straw, but plastic straw, not like a reusable glass straw. You'll need some kind of plastic cap. From any cap is fine. And you will need a woolly sweater as well, right? So we're looking at a lot of similar interactions between plasticky type things and woolly, furry type things. The last option is called electric dill, and so for that you're going to need, again, vegetable oil, dried dill seeds. So this is dill seed, right, from my spice cabinet, and they're quite lightweight little, lightweight little seeds. I'm thinking that you could also use anything that's similarly light. So I happen to have celery seeds. That's a little bit more powdery than the dill seed. You can try different spice jar options as long as you've checked with your kitchen manager, parental unit, or whoever else is in charge of your kitchen before you take expensive spices. So my idea there is that you're going to find things in your own home, find things on a walk. Like, I live close to some construction areas, and it seems like there's always little pieces of PVC pipe laying around. And you're going to conduct your own experiment at home. And then on Tuesday, we'll talk about what you did. And if you can take a picture or a video of it, or if you can prepare it ahead of time to share with us live, that would be great. Okay, let's see. Other things you can use. So I think you can always exchange PVC pipe for balloons, for foam insulation. You'll have to try them all out. But if you don't have a balloon, go for insulation. If you can find like foam insulation from a package you've received, or a PVC pipe like for sprinklers. I think you can always exchange wool or woolly type things with hair, with your own hair. Every once in a while my cat jumps on the counter. I was hoping she would be up here and I could try using her for an experiment. I actually used to have a piece of rabbit fur to use for these experiments, but my dog ate it last week. So wool, hair, fur are all pretty interchangeable. Oh, I missed one. Push a can. Push a can, you need an empty soda can and a balloon or similar. Okay, so I'll cut and paste this all together, and I'm looking forward to our live session next Tuesday.